mostly about this recent paper with Main Christophs at Harvard and Subio Sachdev, who is visiting IIS this year. And I'll also mention briefly some work from earlier this year with Tarek Anous, who was a postdoc in Amsterdam. The motivation for studying this is that many of the recent discussions in ADS-CFT have to do with disorder and various notions of averaging, ensemble averaging. So this started with the realization that JT gravity describes the low energy dynamics of a SYK type ensembles. And this has been generalized in various ways to higher dimensions by considering ensembles of conformal field theories or averaging over microcanonical energy windows, or looking at the statistics of OPE coefficients and all these different things. And on the gravity side, this is related to replica wormholes and various discussions in that direction. So clearly it's desirable to understand properties of such disordered systems and of ensembles of systems, and how we should think about them in gravity. And today I'll speak about a different property that hasn't really shown up in these discussions so far. So I'll begin with some introduction, and then I'll speak about this random SUM Heisenberg model that we studied with Main and Subir, and I'll give some ideas about a potential holographic interpretation. If I have time, I'll speak briefly about the different model, which has some similar features. Right. So I'm assuming that everyone here has some familiarity with the SYK model, so I'll just very briefly recall a few of the features that will play a role. So in particular, so it's this model of n Majorana fermions with random disordered couplings, and its solvable model of holography in the large n limit. This solvability usually, so two of the important things it involves is a mean field description in terms of a g variable, which is a bilocal two-point function of fermions, and understanding the symmetries of the model that involve an emergent reparametrization symmetry at strong coupling that is broken by the saddle point to SO2R. And reparametrizations around this saddle point are also not quite a symmetry. They cost an action, which is this Schwarzian action, which also shows up as the action describing the boundary degree of freedom for a certain type of dilaton gravity in ADS2. Now, because the effects of the Schwarzian action are enhanced at low temperatures, much of the physics in that regime can be understood from this point of view. So for instance, something I will discuss is this somewhat non-standard thermodynamics. There is an extremal ground state entropy, and then there's a contribution that's described by the Schwarzian, which is extensive in n and linear in temperature. Similarly, another observable of interest is this out-of-time order four-point function, where the Schwarzian describes the leading behavior of the exponential growth in the connected piece. Okay, so what is a spin glass? The SYK model is not a spin glass, but many other disordered systems that at the level of the Hamiltonian look quite similar behave in a very different way at low temperatures. So a very different way from what I just described. So the basic idea is, so one of the most famous models is this Sheringham-Kirkpatrick model. We just have classical spins with random disordered interactions. And then you can sort of gain the intuition that the basic thing that happens is that because you have all these random interactions, it's very difficult to find the ground state of the system to minimize its energy. So more formally, whenever there's a loop in the space of couplings between these spins, where the products of couplings are negative, then it means that you cannot satisfy all the energy constraints that you would like to satisfy. And what this means is that the free energy landscape ends up being very complicated. So we have in mind, so this is just a cartoon, it's not precise. We have in mind some free energy landscape as a function of where we are in the space of spin configurations that is very complicated and has lots of values and barriers in between them that at finite temperature would, so these values would become very deep at low temperature. So the system, what happens for systems like that is that they essentially get stuck in one of these values or ergodic components and they lose the property that they explore all the phase space. Or at least they take a very long time to leave their state, and they basically get stuck there for a long time. So relaxation times diverge, and the dynamics slows down over many orders of magnitude. Okay, so of course this is a very complicated situation, but one of the things that Parisi got the Nobel Prize for is the fact that we can actually understand some features of such complex systems. So by one thing is, so if we want to characterize the phase, this glass phase, we cannot use one of the usual order parameters like mean magnetizations because there is no spatial order in this random configuration of spins. So we need to look at something different, and what we look at is something like some kind of temporal order parameter. Because of this feature that I just mentioned, that dynamical quantities take a very long time to equilibrate. So, for instance, you can consider the 2-point function of these spins, and this overline means average over the couplings, and define and look at the long time limit of such a 2-point function. Now, under this averaging, this long time limit will factorize, and you just get 1-point functions squared. It's important that it's a square. If it wasn't a square, you would not get anything interesting. So that's why we have to look at 2-point functions. And in this spin glass phase, the 2-point function will decay to some finite value. So this will serve as one of the important order parameters that I will discuss. So when this long time limit of the 2-point function is non-zero, that tells us we're basically stuck in one of these states. So the goals of this talk or of this line of research will be to first understand what are the characteristic features of this phase. So I mentioned a few of them right now, and then in particular understand the low temperature properties with AdS2 in mind, such as the fate of the zero temperature entropy, the fate of this symmetry breaking pattern, and perhaps study more complicated quantities such as Lyapunov exponents. And then eventually understand what we find in the context of this AdS2 holography. So for today, I will consider two quantum generalizations of this simple model. And most of the time I'll be talking about this one, where we replace these classical eigenspins by spin operators. And the physical case we have in mind is spin 1/2 SU2 operators. But what we will actually consider is something more general, where we consider SUM spin operators for reasons that will become clear. And it will turn out that this model is very closely related to the complex SYK model. And we can study this spin glass physics analytically in a certain way of thinking about this model. And what I also will try to talk about is a different model where we consider bosonic rotor degrees of freedom that basically parameterize the sphere. So it's a nonlinear sigma model with a spherical target space for bosonic degrees of freedom. And this model is motivated by higher dimensional, by certain brain constructions. All right, so I'll talk now about this model, which we started in the So as I said, we replace, so we consider random disordered interactions between SUM spin operators. And to really specify the model, we have to specify a representation that realizes the states on each side. The representation that I will consider is, so in this spinor notation, we write these SUM operators in terms of fermions F alpha, subject to a certain constraint. So for the M equals 2 case, for the SU2 case, this would just be the usual spin 1/2 representation for SU2. So I will refer to these Fs as spin-ons, or also as fractionalized degrees of freedom, because they're only the fractional building blocks of these S spin matrices. Something I'm introducing by writing these SUM spin operators this way in terms of fermions is that there will be a U1 gauge invariance, and much of the physics we can understand by thinking about the properties of that. So because these spin-ons will carry a U1 gauge charge. Now, to study the model, the basic idea, so I'll outline some steps in a second, but there will be a few equations. So let me first tell you the basic idea is to always study large n. Okay, there's two parameters, n and m. N is the number of sites, and I will always take large n first. And then we will consider the large m limit, because that's where we have good analytical control. And in the m to infinity limit, we will find the equations of the complex SYK model. And in fact, that was studied by such different year in the 90s. And I will then discuss, however, finite M effects. And those will introduce this glassy physics. Okay, so let me tell you in a little bit more detail how to do this. So something we want to compute first is the free energy of the system. So log z, where z just involves this interaction that I described and the usual kinetic term for these fermions. And in addition, a Lagrange multiplier term, which implements the constraint. Now, the free energy we expect to be self-averaging. So the average of the free energy should closely resemble the physics that we see in the individual realization of the couplings. But
sorry, maybe you said why do you have that constraint?
So the example to have in mind is SU2, and then the constraint would just say that there are two types of fermions, but you can only, on each side, you can only have one of them.
But here you're exciting m over 2, which seems to say that the representation is the m over 2 antisymmetric tensor of SUM.
Yes, so we have m over 2 rows. Yeah. Okay, so f is self-averaging, but z is not. So we cannot take log of average z, but we really have to compute the average of log z, the quenched free energy. And the way we do this is by using the replica trick. So we write log z as the limit of the derivative of powers of z, because powers of z, we know how to do the path integral. And so this means in all my degrees of freedom, I will introduce replica indices A that run from 1 to little n, the number of replicas. And now we do something that's familiar from discussions of similar models like the SYK model. So we introduce a bilocal collective field for these spin-on degrees of freedom, GAB. So it's a matrix in replica space, and it's bilocal in time. And in addition, we introduce a self-energy field and the Hubbard-Satonovich field. So the canonical way of dealing with this kind of path integral is that we integrate out first the disorder. And so we now want to disorder average all of this. So we replicate it, and then we integrate out the disorder. That's a Gaussian integral. So it will give us quartic interactions between these S. And we decouple these quartic interactions by introducing a Howard-Satonovich field. So that's where we need Q. And that decouples the quartic interactions and essentially gives us a single site description of the problem with an overall factor of n. Okay, so here's what you get. So if you do this procedure, you integrate out the disorder and then the fermions, then you get a G sigma formulation of the theory, or in this case, it's a G sigma Q formulation. And it has a large n effective action. So I'm taking the large n limit. And the large n effective action has this quadratic term for Q. And then it has this single site partition function ZF. The single site partition function itself involves a path integral that we will need to solve. So this is a G sigma path integral that looks very familiar to what the G sigma integral in the SYK model would look like. So this is the large n effective action. There's an associated large n saddle point equation, which tells us that QAB that comes from up here is essentially given by the 2-point function of G with respect to this auxiliary action I. that involves the logarithmic determinant, the Lagrange multiplier, and the interactions. Okay, so this is the large N problem. Now I'm going to take the large M limit, M from the SUM symmetry. So I will evaluate this auxiliary single side path integral for G and sigma in the large M limit because the action here has an M up front. So that's why this will be doable. And I will consider first the saddle point and then fluctuations. So finite M effects. The saddle point equations at large M in this problem. So these are self-consistent equations for G, sigma, and Q, for these collective variables. And again, if you're familiar with the SYK model, these equations might look very familiar, except for the fact that I haven't gotten rid yet of the replica indices. So everything is still matrices in replica space. Now, GAB was the 2-point function of the fermions, of these spinons. So GAB cannot have any replica off-diagonal terms. That would factorize and would give you 1-point functions of the fermions, but so that the fermions cannot condense. So GAB has to be replica diagonal. But if you put that information into these equations, then you see that everything has to be replica diagonal. So I can focus on the diagonal terms in these matrices. And then the replica diagonal parts of these equations are precisely the equations of the complex SYK model. So at infinite M, we find exactly the equations of the SYK model. And you're presumably familiar with the physics of these equations, all the various connections with quantum gravity. But now we want to understand what happens at finite M if we consider 1/m corrections. And before we do that, let me just tell you what you find if you put the problem on a computer, say. So first consider again the infinite M limit. And let's look at this Q variable, which was the 2-point function of the spins. So it's like a 4-point function of the fermions. And we consider the spectral representation of that. So the spectral function, susceptibility chi, which has the following form. So the leading behavior in frequency space is just given by a constant proportional to the sine of the frequency. That's the conformal long time behavior that has been understood a long time ago. And then more recently, it was understood that the correction to this is described by the Schwarzian action. So this is like the graviton contribution to this spectrum. And then various higher order terms have been computed, for instance, in this paper down here, where I took the figure from. So this is what you find numerically. So you can see that this is a gapless system which has a finite value for the susceptibility at 0 frequency. And then you can see this linear and omega behavior in various corrections to it. But if you solve the equations for finite M, which was done here basically, you'll find something different. So you'll find that at low frequencies, the density of states gets suppressed. So this SYK density of states gets quenched, and we don't get this finite spectral density anymore. Instead, all these low energy, but these low frequency excitations accumulate in a delta function at 0 frequency. And this is basically the frequency space version of what I described before, that the 2-point function has a constant term to leading order, so it will decay at long times to a constant. That's basically what this delta function tells you. So what we want to do is understand these features analytically in this fermionic description that I introduced. Okay, so let's do that. So we go back to our G sigma Q formulation in replica space. And if we now consider 1/m corrections, then these don't have to be replica diagonal anymore. So we make an ansatz for Q, and we let it have replica off diagonal terms. So first we let it have a constant term in the replica diagonal, That's the long time value of the 2-point function. And then we also allow for constant terms for off-replica overlaps between different replicas. So this matrix of constants will be our order parameters for the spin glass fix. And we expect them to be small because at infinite M, there was no spin glass order. So we expect these order parameters to be small, and we can do a perturbation theory in these order parameters. So we can compute the large N action that I described perturbatively in these parameters. And to see when the onset to spin glass order happens, we can just consider the stability of the system towards these kind of fluctuations. So we look at the quadratic action, quadratic in these Qs, and see what's the coefficient. Now at infinite M, you see that the coefficient is just 1, so that's fine. But then, as we include one over M effects, you can ask what happens if I plug in here the Q that you would get in this SYK phase. That Q was like was the 2-point function of the spins, so it goes like GG in SYK language. And so if you translate that to frequency space at 0 frequency, you'll get some expression that's logarithmic in the temperature, and that translates. And that means that this coefficient becomes 0 at a particular critical temperature. So if you do that exercise, you find that this temperature is exponentially small, but in M, not in N. So even for M equals 2, it's quite small, but it's very much finite.
Sorry, what is the Q hat? That's a 0 mode of Q.
Yeah. Okay, so at this temperature, this spin glass order sets in. Now we can look at the problem in some more detail and look at the free energy. I described how you can compute the free energy, and if you compute the free energy order by order in this perturbation theory, in these Q parameters, you basically produce. This is some Landau functional where you produce basically all terms you could possibly produce. So I didn't write down the coefficients here. You can compute all of these coefficients, but the point is just you produce all possible terms at various orders in 1 over n. But some of them, the ones that I drew in blue here, they seem dangerous because they're proportional to explicit powers of beta. So as we send beta to infinity, the temperature to 0, these terms you would think will diverge, and so that's not good. That would mean an inconsistency. So we have to find a solution for these order parameters Q, for which the free energy is not pathological. So it's finite at 0 temperature, and in fact, you can do this just by extremizing the functional with respect to these parameters, and then you find a solution which makes all these blue terms vanish in the replica to 0 limit. At 0 temperature, this is very simple. This is just all the Q parameters you set to the same value, which is this Edwards-Anderson order parameter. And then in the little n, the number of replicas, if you set that to 0, all the blue terms will go away, and the free energy is finite. At finite temperature, you have to do a little more work. So then you do this Parisi ansatz, which is a particular structure for how replica symmetry is broken. So we need to figure out an ansatz for this QAB matrix, which we can analytically continue to n to 0. N is the size of this matrix. Or actually, so it's, in some sense, we first take n to infinity. We construct a very large matrix, which has some iterative structure that actually allows us to take the n to 0 limit afterwards. And the solution that gives you consistent free energy has this block form that has constants off the diagonal and then identical blocks along the diagonal. And each of these blocks has the same structure, with some constants and then blocks along the diagonal, and you keep going like that and construct an infinitely large matrix with this structure. And in the limiting case, when you make this matrix infinitely large, you can just describe the structure of how these constants get smaller towards the diagonal in terms of a continuous function on from 0 to 1. And just by extremizing the functional and seeing what's the right function, you find that this function is piecewise continuous. So it's continuous. It's just a linear and then a constant. So it levels off at this Edwards-Anderson order parameter, and the place or the value where it transitions is some other parameter m that plays a role. Will show up later again. So there's this, basically just two parameters which tell you the features of this function: the plateau value and the break point where it transitions into the plateau. Okay, so let me get back to the thermodynamics and specifically to the entropy. So the fact that the density of states, this spectral function, went to 0 also implies that there's no extensive entropy at 0 temperature anymore. So whereas while in the SYK model we understand in great detail now how this entropy behaves all the way down to very small temperatures, in this model we expect that at the critical temperature the entropy will drop off and go to 0. And this raises a puzzle. So how can this be? How can the entropy vanish if there are supposed to be exponentially many states in this complicated free energy landscape? How can that be? So the answer is that we have this cartoon of the free energy landscape, and in this glass phase we're stuck somewhere, and the system has lost its ergodicity, so it's not exploring all the rest of this configuration space anymore. And the thermodynamic entropy that I told you goes to 0 just tells you about the fluctuations within this valley. So what we should do is we should also count the number of valleys with a similar free energy if we want to really understand the full entropy of the system at some value of the free energy. And the way you do this is as follows. So we're going to decompose the phase space or the Gibbs measure into components associated with all these values, separate ergodic components, and we imagine that the entropy is the sum of all the entropies we get there. And in the large N limit, it's then natural to introduce a density for these values. And the exponential of this, so this density we write there is an exponential, and the exponent we call the complexity. This is a different complexity than what we've heard about today. Nothing to do with that, or at least nothing obvious. Okay, so then we can compute the total partition function, or the total free energy, as an integral over this density, the free energy of any particular value, and then the density of these values. So we can define some generalized free energy, which is the original free energy minus the complexity, which tells us about the density of these pure states. Now, this is like standard thermodynamics. So in the large N limit, you can evaluate this integral by saddle point. So you find some saddle point equation for the free energy. And by this kind of reasoning, you can basically compute it. So this is very similar to standard thermodynamics, where this generalized free energy plays the role that would be the free energy in thermodynamics, and the free energy now plays the role of energy, and the complexity plays the role of entropy as an analogy.
Sorry, the free energy of the replica trick is which of this?
F. That's our original free energy. Okay, now not going to go into this, but using replicas and pinning copies of the system to the same state, you can show that the complexity can be computed like this from the free energy, the one that I mentioned. And again, this is somewhat analogous to standard thermodynamics, where the entropy would be given as the minus the temperature derivative of the free energy. So this gives us a practical way to compute this complexity. And what we find in this model is some value which involves the coefficients from the free energy. So this value doesn't really matter what it is, but the point is it's finite at 0 temperature. Okay, this is as beta goes to infinity, it gives some constant value. It's also proportional to this Edwards-Anderson order parameter, so it will go to 0 outside of this spin glass phase. So this resolves this entropy puzzle, that all this entropy that we had in the SYK state has been transformed into the complexity, into an extensive, so extensive in N up here, complexity of this landscape of states.
Is it numerically equal to the ground state entropy of the SYK, or is it something?
Oh, that's an interesting question. I don't know. So, yeah, for that, we would probably have to do some numerics. All right, so I'll have like 2 or 3 minutes, so I'll be brief. If we want to try to interpret this in holography, we need some suitably disordered geometry. It doesn't have the translation invariance or homogeneity of a black brane, but we need something more complex that somehow resembles this large landscape of states that I described. How can we accommodate for that in holography? And so there has been work on this in these various papers, and the hint is that in 4D supergravity, there exists a landscape of multi-centered black holes, black hole bound states. And in these papers, they looked at finite temperature versions of these in AdS and found that there are again these bound states of multi-centered black holes, such as this one, where you have some heavy central black hole and then many probe black holes around it. And these are, so as far as I understand, these are not equilibrium states, but they're still metastable states, like our glass states, that have a very long relaxation time. And now we want to study this in this simpler model, like the one I described, where we expect some connection with AdS2 gravity. And there's something similar that happens in AdS2, which is this fragmentation instability that was studied by the same Michael Strominger and others. So this is saying that if you consider the near horizon geometry of 4D Reisman-Nordstrom black holes, you get the usual AdS2 geometry, AdS2 times S2 geometry. But there are more complicated solutions that flow to multiple throats. And these arise from solutions to 4D Einstein-Maxwell theory with multiple centers. So at large X, you would discover the same geometry as with a single throat, with more charge, with the charge of both of these throats. But as you flow into the geometry, you will discover fragmentation into multiple AdS2 regions. So one way you can distinguish the geometries from far away is by considering or by measuring something like an average dipole moment. And the suggestion would be that this is very similar to this Edwards-Anderson order parameter that arises in the 2-point function that I discussed. And we would like to suggest that the moduli space of these geometries that are parameterized by the charges and the locations of these various throats seems very similar to the space of states that I described in the theory of spin glasses. Okay, I think I'm out of time. Is that right? Another step. Yeah. Okay, so I'll skip this. So this is this other model that we studied with Tarek, where we also computed things like complexity. That's again finite at 0 temperature, and we see many similar features. And we also computed some 4-point functions and Lyapunov exponents in the spin glass phase with that model. It would be interesting to understand from a gravity point of view. Okay, so here's the summary slide. So I told you about this model of random disordered couplings between SUM spins. In the infinite M limit, this reduces to the complex SYK model, and the 1/m corrections give us an analytic handle on weak spin glass order. So we could analytically understand that the transition in the spectral function from this high frequency state that's like the SYK spin liquid, where the spin-on degrees of freedom are deconfined, to the low frequency regime, where the U1 H symmetry that we had in this description is confined. Okay, thank you.
I assume the valley states don't all have the same energy. Does part of the theory give the distribution of energies of those states?
So you're right, they don't have the same energy. So
Yes.
so we characterize them by the free energy, and there's a spectrum of that. To figure that out in detail, I think that's a more microscopic question. Study something like there are certain equations one can write down for all the magnetization, the mean magnetizations of all the spins, and those give you some information about that.
So Parisi ansatz actually implies that these pure states you mentioned, they have certain ultrametricity structure. So can you see how it arises holographically for gravity?
Yeah, that would be an interesting thing to look for. So this ultrametricity you're mentioning occurs in the case where we have this full replica symmetry breaking, the Parisi ansatz that I described. There are simpler models like this p-spin model that I didn't have time to describe, where you don't need to do that much replica symmetry breaking, but one-step replica symmetry breaking is enough to get a consistent solution. Meaning that, so you do this, you write this matrix with blocks along the diagonal, but you only do this in one step, and then you're done. So that's probably a simpler case to study first, where the structure is not quite as complicated.
Further questions? Anyone online with a question?
Can they hear when you ask that?
They should be able to hear me when I ask if anyone online has a question. But no one's replying to verify that. Yes, clarification. Yeah, it's not, I have a question. Do you know if there's any connections between this this quantity you're calling complexity to kind of characterize local minimums of energy then, and something called the overlap gap property that comes up in, this is something that comes up in kind of algorithms for trying to solve these spin glasses or find the actual minimum. And when problems have this property, it can make it very difficult for certain classes of algorithms. So I'm just wondering if you have heard about it.
I've heard of it, but I'm not. I don't know very much about it.
Let's take it again.